Now that we have phasors, we're able to analyze AC circuits, or circuits with AC inputs. Let's go back to superposition. Prior with DC, we were showing that if you have a circuit with two separate inputs, you can treat that as two separate problems. The total response will be the sum of the two. Back at DC, that was rather silly, because you might as well just analyze this whole circuit at once. Now that we have sine waves coming in, this is where superposition really shines. What superposition says is that if I have a linear system, I can split it up as two separate problems. In English, what that means is that if I have an input, which is made up of three separate terms, what I can do is pretend I actually have three separate circuits, each with a separate input. Each of these three I'll analyze separately. The total output will be the sum of those three outputs. So the circuit on the left is what you actually build. The circuit on the right is how you analyze it. And we can analyze it using the properties of superposition. For example, probably the best way to explain this is to give an example. Suppose I had a circuit right here. This is just a low-pass filter, one we talked about a little bit before. And suppose the input has three separate terms. I've got a DC input of 10 volts, 100 radian per second input at 9 volts peak, and a 200 radian per second input at 8 volts peak. Find y of t. The solution is to treat this as three separate problems. One, ignore the two frequencies and just assume x of t is 10. Analyze the circuit. Now pretend the input is just 9 sin 100t. Now analyze the circuit. And again at 8 cosine 200t. Each of those circuits is different. The inductor is j omega L. If the frequency changes, the inductor changes, the capacitor changes, the input changes. So those are three separate problems. The total output will be the sum of those three outputs. So starting out, at DC, I'll take the input, analyze the circuit take the input at DC, which is 10 volts, analyze the inductor at DC, which is j omega L, at DC omega 0, so L is 0. The capacitor is an open circuit, so I just have a voltage divider. By voltage division, the output is what I'm measuring, 2000 over the total times the input, 8.77 volts. That's the output at DC. Now, analyze at the next frequency. At 100 radians per second, the input is 0 minus J9. Again, 0 is the real is cosine, minus J is sine. The frequency is 100, that's this term right here. The inductor becomes j omega L, J1000. The capacitor becomes whatever j omega C, minus J5000. Now analyze this circuit. If I put the resistor capacitor in parallel, I get 1724 minus J689 ohms. Now using voltage division times the input, I get the output. Output is minus 4.2 minus J7. That's at 100 radians per second. Third, analyze the circuit at 200 radians per second. Now the input in phasor form is 8 plus J0, 8 cosine, 0 sine. The frequency is 200. That's this part of the cosine. The inductor becomes J2000 ohms. Capacitor becomes minus J2500 ohms. Analyze just like we did before. Put these two in parallel, gives you 1219 minus J975 ohms. Then R1 over R1 plus R2 gives you the answer. And the answer is 2 minus J6.5. The total answer then will be the sum of the three. This is where people tend to make mistakes. I've got three complex numbers. They want to add them together. You can't. The first one is at DC. The second one's at 100 radians per second. The third one's at 200 radians per second. What these phasors represent is a DC term, a 100 radian per second term, and a 200 radian per second term. These don't simplify. You're still left with three different terms. And that kind of makes sense. If the input has three different frequencies, the output has three different frequencies. That's what superposition is really used for. If you have a circuit where there are three different frequencies coming in, treat it like three separate problems. The total output will be the sum of those three outputs for each separate problem, and that's superposition.